Hello, everyone, and welcome to the first webinar in the series of IAEA webinars on nuclear technology breakthroughs in the 21st century. Today's webinar is on nuclear renewable energy, integrated energy systems, their prospects and issues. My name is Matthias Krause, and I'm a member of the water-cooled reactor technology development team in the Division of Nuclear Power at the IAEA. Our initial announcement included Ms. Tatiana Čevremović, our team leader, as the moderator. However, she was called to an urgent and important internal assignment, so she could not be here right now. So today it's my pleasure to run this first webinar in a series of IAEA webinars with the goal to exchange information with our member states on how the current and future sustainable nuclear energy systems can help address the growing energy demands as well as the goals to limit climate change around the world. So in today's webinar, we will be addressing how the combination of nuclear and renewable technologies, not as competitors, but in a synergistic way, can leverage the benefits of both technologies to provide reliable and sustainable electric power to the grid, as well as low carbon energy to other sectors. Now we have nearly 400 registrants today, and this clearly reflects the great interest in today's topic. So before introducing the speakers, I have a few housekeeping items to address. This is a live and interactive webinar, and we would love to hear from you. So if you have any questions, please type them at any time into the Q&A panel, and we will try to address them as many of your questions during the question and answer session after the two speakers. Please also use the chat panel in case you're having technical difficulties. Any problems that you're experiencing with the connection, and our technical team in the background will try to help you out. All participants will remain muted for the duration of the sessions. Therefore, if you have any questions, please type them in the Q&A panel. After the webinar, recording along with the presented will be available online. Presented material can be made available by if you contact me directly. And finally, please note that the IAEA is not offering certifications for this webinar in this series. Now let me introduce our speakers. Our first speaker, Shannon Briggs-Sitten, will get us started by introducing the concept of integrated or hybrid nuclear energy systems, briefly covering the motivation for developing these innovative systems and examples of near-term demonstration projects that are already underway and will pave the way for integrated systems that incorporate SMRs and other advanced reactors. Then our second speaker, Dr. Kamil Tuček, will discuss the European perspectives for more synergistic integration of nuclear and renewable resources, covering the EU policy context and associated drivers related to the expected evolution of the energy mix, giving also some examples of ongoing activities and related R&D needs. So let me introduce our first speaker, Dr. Shannon Briggs-Sitten, in some more detail. Shannon is the lead for Integrated Energy Systems IES at the Nuclear Science and Technology Directorate at Idaho National Laboratories, or short INL, in the United States. With this role, Shannon serves as the co-director for the INL laboratory initiatives on IES, which includes focus areas for thermal energy generation, power systems, data systems, and chemical process and industrial applications. Shannon is also the INL lead for the DOE Applied Energy Tri-Laboratory Consortium, which includes INL, the National Renewable Energy Lab, and the National Energy Technology Lab. Shannon has held multiple leadership roles in the DOE Office of Nuclear Energy Programs since joining INL in 2010, ranging from space nuclear power and propulsion systems to advanced nuclear fuel development to her current work in the integrated energy system design and demonstration. She currently serves as the National Technical Director for the DOE nuclear energy IES program within cross-cutting technologies development. Integrated energy system designs seek to coordinate the use of multiple clean energy generation sources, such as nuclear and renewables, to meet both thermal and electrical energy needs. Shannon holds a PhD and Masters of Science in Nuclear Engineering from the University of Michigan, a Master of Science in Medical Physics from the University of Texas at Houston, and a Bachelor of Science in Nuclear Engineering from Texas A&M University. Now over to Shannon.
Thank you so much for that introduction, Matt. So I'm really excited to be here today to be a part of this kickoff webinar in this series on nuclear technology breakthroughs. I do believe that integration and coordination of nuclear and renewable energy sources is truly a breakthrough opportunity for clean energy systems, both now and in our future energy systems. Before I go into that in detail, I do want to provide a little bit of context as to where nuclear energy is currently in the United States. Nuclear energy provides just under 20% of our electricity supply in the US, but as of 2018, nuclear energy provided more than half, 55% of our emission-free electricity. That's pretty phenomenal, especially when coupled with a fleet-wide capacity factor of 92.6%, meaning that nuclear energy truly is reliable, resilient, and dispatchable, available when we need it. However, our nuclear energy systems are currently suffering some economic challenges due to the advent of lower cost renewable generation systems and historically low cost natural gas. These new entries to the electricity market do cause some fundamental changes in our grid dynamics and are challenging some of the way our nuclear systems operate. Going to my next slide, I'd like to highlight some of the recent studies in these systems. The MIT Future of Nuclear Energy study was completed in 2018. Some of the key findings in that found that as the world faces these challenges of drastically reducing emissions of greenhouse gases, we're simultaneously seeing some expansion of energy access to billions of people. While electricity demand may not be increasing in the US, it is in fact increasing in other nations around the world. As we look at the different options for low or zero carbon technologies and the combination of those options to meet that demand, we see that without contributions from nuclear energy, the cost of achieving deep decarbonization targets increases significantly. And the least cost portfolios always include a very important share for nuclear. And as the cost for nuclear energy itself drops, that share increases. So some of the fundamental challenges that nuclear is seeing is cost, as well as energy policies that exclude nuclear energy from contributing to clean energy standards in some countries, as well as some of the public perception challenges. I apologize, it looks like my slide is coming up strangely on this computer. The second report, these slides will be made available, I apologize for that. The second report I'd like to highlight is from the International Energy Agency, and that was released in May of 2019. In that report, I find it astonishing that the data shows significant growth in renewable generation and the deployment of those renewable generators over the last 20 years. But the overall contribution of clean energy supply or non-emitting generation fundamentally hasn't changed. And this is because of the advent of low-cost natural gas in many countries around the world, particularly in the US, we see this. And the fact that natural gas turbines are scalable and allow for very rapid ramping, making them an easy complement to wind and solar that are changing those grid dynamics that I mentioned. So where does this bring in the coordinated use of nuclear and renewables? When I think about designing our future energy systems, I like to take a step back. Rather than asking the question as to what each of these generation sources can do, I like to first make sure we're on the same page when we think about the goals that we're trying to achieve with these energy systems. I think we can generally agree that we'd like these systems to be reliable. They need to be resilient to weather events, to man-made events, etc. They should be sustainable and they should be affordable. We're now also bringing in the goal of low carbon emission, or clean energy technologies. The next question we need to ask is how that energy will be used. Is it purely to meet electrical energy needs, or do we also need to be concerned about energy needs for industrial applications that may require heat or steam to meet those needs? And how flexible are each of those demands as we look across the various energy use sectors? Finally, we can now begin to ask that question as to the role for each energy source. How will nuclear energy technologies work alongside wind, solar, hydro, fossil fuels with carbon capture and sequestration? And what size of nuclear system is needed? Is there a need for a large-scale, gigawatt-scale system, or perhaps only a megawatt-scale system? This brings me to the concept of integrated energy systems, which is the topic for today's discussion. When we think about designing these integrated systems, we have paramount importance is using energy effectively and efficiently. And I like to think about this as highly efficient use of our capital investment to put these energy systems on the ground. Rather than throw away heat that isn't converted to electricity, how do we use that better? How do we more effectively use the heat, electricity, and steam to meet the various needs using the generators that may be applicable in a particular region, such as fossil, nuclear, or renewables, to meet the electrical grid demands in a dynamic, variable fashion as we see net demand changing? How do we meet the needs in industrial applications that are in that particular deployment region? Perhaps this is an island nation or a desert region that needs water purification as well. We can even begin to think about how we reinvent chemical processes to better match up with these energy generation technologies, such as nuclear energy, where in some cases radiation itself could be an asset to those chemical process reactions. We also focus a lot on hydrogen and how hydrogen can be utilized as an energy storage device, a mobile energy carrier that can be moved from one place to the next for later electricity production or for the production of transportation fuels in fuel cell vehicles or synthetic fuels that burn cleaner than our current fuel systems, or how it can be used in other technologies as well. And we'll say a little bit more about hydrogen as we go forward. And when we look at the nuclear energy options we have available, what we have today is very different from what we may have had 20 or 30 years ago. We, of course, have our large-scale light water reactors that make up most of our current operating fleets around the world. But now we also have the advent of small modular reactors, where each of those modules is less than 300 megawatts electric and can meet many different needs. We have micro reactors that may be on the megawatt or a few megawatt scale, and advanced reactors that bring in higher temperature applications that may better couple to some of these various applications around the circle I show here. In the US, we are looking forward to our first small modular reactor in the mid-2020s. That will be an integral PWR design. We're also looking toward a demonstration of our first micro reactor here at the Idaho National Laboratory site by about 2025, and as many as 2 advanced reactor technologies being demonstrated by 2028 and 2 more by 2035. We see so much investment and so much going forward in new nuclear technologies that vary our options in these integrated systems. We're beginning to see that these integrated applications of nuclear technology really provide a key opportunity for enhancing our flexibility of nuclear systems. Currently, we have many nuclear plants around the world that provide operational flexibility, varying their power output to meet variable demand that may be due to simple demand changes or due to more and more renewables on the grid that create a more dynamic net demand. But we can also look at product flexibility, where nuclear energy works alongside these chemical plants and renewable generators in integrated systems, providing product flexibility where that thermal energy can be used to create many diverse products, some of which are listed here on the right. Clean water, hydrogen we've talked about, ammonia production, metals refining, just to name a few. And finally, we are beginning to see more and more of the size flexibility of these nuclear systems, such that we can see how these work with not just large communities and municipalities, but very small remote communities that may rely on a more mobile power source and meeting needs that are much smaller than we typically think of for nuclear systems. So now I'd like to tell you a little bit about some of the exciting opportunities that are going on in the United States These integrated systems aren't just paper designs or computational designs. These, in fact, are moving toward demonstration. We are working with industry, we being the national laboratories funded by the U.S. Department of Energy, have been working with industry to characterize, to understand how these systems might operate, to model potential applications of nuclear energy that are beyond just electricity production. And the example I show here shows the production of hydrogen via water electrolysis. Now, the incumbent technology for hydrogen production is steam methane reforming, where in its most basic sense, we take methane, we use thermal energy, mostly derived from fossil energy resources, to break down that methane. Well, we produce hydrogen in that process, but it's also a production source for carbon dioxide. So we have a significant carbon footprint through that process. If we instead generate hydrogen by breaking down water molecules via a low temperature electrolysis or polymer electrolyte membranes that occurs just by the use of electricity, we break down that water without emissions. That can be done using renewable electricity or nuclear electricity. We can also look at high temperature electrolysis, where we also use some of that thermal energy supply from a nuclear generator, for example, to achieve even higher efficiencies in producing that hydrogen. Now, that hydrogen can go toward many different things. It can provide energy storage for later electricity production. It can be used in natural gas pipelines for combustion at other locations for electricity production, or it can go to many different hydrogen users. And I've just listed a few here, with chemicals and fuel synthesis, steel manufacturing, ammonia-based fertilizers, thereby allowing nuclear generators to have a second source of revenue when electricity prices are very low or sufficient electricity is available from renewables. We now have another application for that vast amount of thermal energy from our nuclear generator to create revenue for the plant. We also now see how nuclear generators can provide grid services, including reserves and grid regulation. So as I said, these aren't just theoretical projects at this point. We are moving toward demonstration, and I highlight those here on the right, and let's talk about them a little bit more on the next slide. So these demonstration projects are what we call cost share projects, where we have federal investment from the Department of Energy, as well as private investment from the companies working with us for these demonstration projects. Now, both of these projects are focused on initially electrical integration of those electrolyzers for hydrogen production on site at the plants. This provides us a first step to look at co-location of hydrogen generation systems at a nuclear plant site. On the left, we have an Exelon-led project that, again, is working with DOE to first demonstrate a fairly small-scale hydrogen production system for on-site hydrogen use, but then also laying the foundation to move that hydrogen to regional hydrogen markets. This begins to give us an understanding of how these systems operate flexibly in response to the regional market and the regional grid. And on the right, we see a second consortium, an industry consortium led by Energy Harbor, Xcel Energy, and Arizona Public Service. This hydrogen demonstration system will be put on the ground at the Davis-Besse nuclear power plant in the US Midwest. And in this case, again, it is an electrical tie-in to the plant, but working with a different electrolyzer company and working within a different energy market, such that we see different dynamics that the hydrogen production system will have to respond to. Now, the engineering design team is focused on designing and locating the equipment for hydrogen production such that the effect of the design and licensing basis is mitigated so that we don't have significant challenges associated with getting regulatory approval for performing these projects. Now, both of these projects will be putting steel in the ground, hardware ready to demonstrate within the next 12 to 24 months. We are in the true engineering design phase. I'm really excited we'll begin to see hydrogen coming out of these projects within a very short time. Now, I don't want you to begin thinking that this is just going on in the US. We'll hear from my colleague on work in Europe here shortly, but I want to highlight an international effort related to this that's also ongoing. Let me first introduce what the Clean Energy Ministerial is. Now, the Clean Energy Ministerial is a high-level global forum that promotes policies and programs that advance clean energy technologies. It currently has 25 countries that are members of the CEM, as well as the European Commission. And the SEM includes many different initiatives associated with this overarching goal. The Nuclear Innovation Clean Energy Future Initiative was first launched in 2018, and this was the first nuclear initiative under the SEM, and this was introduced at the 9th meeting. This was overdue in my perspective. This initiative explores the potential uses for nuclear energy, innovations, and greater systems integration like we're talking about today in order to accelerate our progress toward these clean energy goals. The initiative does recognize that there is no one-size-fits-all. Some countries looking at this may choose not to select nuclear energy to meet their energy needs. However, we do want to foster collaboration among these clean energy supporters, and we want to encourage them to explore diverse solutions that include nuclear technologies, ranging from the small megawatt scale systems now that will be available very, very soon, as well as the larger scale systems that we see today. Now, this initiative was launched by the lead countries shown here, Canada, Japan, and the US, and we have 8 additional countries also participating with us. And I encourage you to consider what Nice Future is doing and to join us as we move forward. We have many external partners shown on the right here. IAEA is one of those partners, and I thank them for hosting this webinar today. Going to the center of this slide, just to highlight some of the focus areas the Nice Future Initiative is working on. The first listed here is really this technical piece that I've been describing on how we utilize innovative applications for advanced nuclear systems, both electric and non-electric applications. The second one, we look at economics, understanding that economic structures are very different in each country, but we share and pool our resources to better understand valuation for energy, and specifically nuclear energy, market structure, as well as the ability to finance these systems, to deploy them in these different locations. Third, we understand that engagement of policymakers and stakeholders is fundamental to the success of these systems. So this is key to future success of deploying these systems. And finally, communications. Communications is foundational to helping people understand what nuclear energy has to offer and how that role can vary as we move forward in our energy system designs. And we also work to engage the nuclear workforce of the future. We want to communicate with students and young professionals considering their potential energy future or career futures in the energy sectors. So as I go to my last slide, I want to leave you with a question. I've given you some examples of what we envision in the US and across some of these partner countries on how we can truly be innovative in how nuclear technology is utilized. But it's up to you. How do you envision meeting future energy needs? Will it be to support naval bases, water purification, remote villages that need reliable energy and power, or industrial applications? And how might nuclear energy that does not emit these greenhouse gases, how does nuclear energy play a role in some of those futures? So with that, back to you, Matt, and I'm excited to hear what my colleague in Europe has to say.
Thank you very much, Shannon, for this very comprehensive and interesting discussion on what's going on in terms of related projects in the United States, and also to talk about a nice future. I've heard about this a few times, and it's a great acronym to pick for this big international cooperation. And just to your last point on your second last slide regarding communication, we're glad to introduce this webinar series. This is just the first of many to come on providing communication at an objective technical level on nuclear technologies and the future that they have in this century. So with that, let me introduce our second speaker, who will be presenting the European overview. Dr. Kamil Tuček is a researcher and a team leader at the European Commission Joint Research Center, Directorate G, which is Nuclear Safety and Security, Nuclear Reactor Safety and Emergency Preparedness Unit, and they're located in Petten in the Netherlands. Kamil received his PhD in physics from the Royal Institute of Technology, KTH, in Stockholm, Sweden in 2000. 1994 and his Masters of Science also in Nuclear Engineering from the Czech Technical University in Prague in 1966. His scientific background includes advanced reactor systems, related material compatibility, and safety assessments, as well as energy system integration in evolving markets. Prior to his current position, he held research posts at the Nuclear Research Center in Rzeszów in the Czech Republic, at KTH in Sweden, and at the Karlsruhe Institute of Technology, KIT, in Germany. So with that, I give you another 15 to 20 minutes. Camille?
Thank you very much, Matt. Thank you for this very nice introduction and also for Shannon's consideration. I'm indeed happy to be invited and contribute to the IAEA webinar series on nuclear technology breakthroughs for the 21st century, and happy also to present the European perspectives on the integration of the nuclear and renewable sources for electricity production and beyond. First, I would like to discuss the context of the nuclear energy in Europe. There are 108 nuclear reactors which are in operation in 13 EU member states. The nuclear energy provides about 25% of the EU gross electricity generation, around 50% of EU low carbon electricity generation, and it supports around 1 million of jobs. In EU, each member state can decide on the inclusion of the nuclear power in its energy mix. We have about 4 new reactors which are under construction, which is in France, Finland, and Slovakia. And there are about 20 reactors which are in different stages of planning and preparation in 8 member states. And now, looking into the future, the nuclear generation electric capacity at EU level is predicted to decline up to about 2025. And this as a consequence of the decisions of some of the member states to phase out the nuclear energy or to reduce its share in the energy mix. However, this trend is predicted to be reversed by about 2030 as new reactors are expected to be connected to the grid, and as we will also pursue lifetime extensions of the current reactors. The nuclear reactor capacity is then expected to increase to about 100 gigawatt electric by 2050, and indeed also significant new investments are predicted both for the long-term operation and for the new build. Now, to meet the climate goals in Europe, it's the objective to ultimately achieve the climate neutrality by 2050. Significant energy efficiencies are envisaged in Europe. And on top of that, the share of the renewables is expected to grow dramatically to about 60% of the gross inland consumption, which is expected to be combined with the nuclear sources having a share of about 10 to 20% in the inland consumption by 2050. In Europe, the climate and energy strategy aims at integration of different energy vectors, electricity, gas, and heat. And this in support not only for the decarbonization of the electricity sector, but also indeed of the industrial, transport, and agriculture sectors, among others. Now in Europe, the European Strategic Energy Technology Plan is an instrument which is driving the implementation of the European Energy Union. It identifies 10 key actions with objectives to reduce the cost of key technologies, to enhance security of supply, among others also improve energy efficiency, as well as to improve the energy system resilience. As one of the key elements, this also includes further development of renewable technologies and their integration with other technologies, including nuclear. Now, with rising proportions of variable renewables, and as already explained by Shannon, an improved optimization of the integration of nuclear and renewables is further opportune. This through cogeneration and possibly also through establishment of a tighter coupling via nuclear renewable hybrid energy systems, or as we call it, integral energy systems. The nuclear cogeneration allows switching between electricity and heat generation, with nuclear power plants still being able to operate at high capacity. And at the same time, variable renewables, which are integrated in these systems, can be less curtailed, and the surplus of the energy can be used to deliver new carbon lean products or services, as, for example, the hydrogen already discussed by Shannon, industrial process heat, hydrocarbons, or district heating service. Such systems can also work well in delocalized markets and support also other policy objectives, including, for example, the improved nuclear waste management through transportation. In Europe, the Sustainable Nuclear Energy Technology Platform, SNETP, implements the set-plan nuclear action. And under the umbrella of SNETP, one of its pillars, Nuclear Cogeneration Industrial Initiative, NC2I, develops new applications of nuclear power based on cogeneration of electricity and heat. And in this context, NC2I also investigates, indeed, a further tight integration of nuclear and renewables in the form of hybrid energy systems. So what I'm presenting to you on this slide is an example of flexible nuclear steam producing boiler, which is being developed by the NC2I, with the objective to replace aging standard coal or gas boilers. There is, in fact, a large market in the EU for process heat applications with temperatures of around 550 degrees C, amounting to more than 80 gigawatts. This high temperature reactor, which is considered here, could be plugged into the existing industrial steam grid using the existing infrastructures. And as one of the discerning features, this reactor is also fully passive, and all subsystems are compact and suitable for road transport. So what are our other options in terms of, and apart from the high temperature reactors, so other concepts which are being developed are SMRs based on the light water reactor technology. Many of these light water reactor SMRs consider novel features, which include the integration of primary components, such as steam generators into the reactor pressure vessel, and also use of passive natural convection command flow. As one example of this development, I display here the design of the FSMR concept, which is being developed by the consortium of partners in Europe, led by French organizations, and is investigated within the European project ELSMO. Furthermore, in generation 4, the reactor concepts which further improve safety and performance characteristics are being investigated and developed, and this includes very high temperature reactors, liquid metal cooled reactors, sodium lead cooled reactors, as well as molten salt reactors, which are considered as options. So what are the research needs that could make these developments a reality? Well, I think we could classify them in principle to 4 overarching domains. These relate to innovative technologies, innovative materials, deployment aspects, and societal policy and regulatory aspects. Further innovation encompasses the development and qualification of the inherent and passive safety features here in practical, and in particular for justification of the reduction of the emergency preparedness zones, as well as development and integration of dedicated components and their prototyping. Moreover, indeed, the development of innovative accident-tolerant fuels and more resilient materials would further improve also the safety characteristics and technological performance. Also in this context, of course, key needs are the cost reductions, possibly more streamlined licensing process, a streamlined supply chain, and improved standardization and harmonization. And fundamental are, of course, the public acceptance and sufficient funding for these developments. So do we have an adequate funding? So to answer this, I would like to conclude with presenting the proposal for the budget of the next Euratom research program, which is expected to start 2021. In this 2.4 billion of euros is envisaged for all Euratom activities, out of which 330 million of euros is dedicated for fission R&D activities related to safety, with additional 620 million of euros dedicated to fission safety and research and safeguards activities at GRC. Moreover, we have budgeted in the proposal 724 million of euros expected for the fusion R&D, and there is also, of course, a dedicated budget which is available to support the deployment of ITER. This is at the level of 6.1 billion of euros. So with this, I'd like to thank you very much for your kind attention, and of course, both Shannon and I are looking forward to responding to any comments or questions. So over to you, Matt.
Thank you very much, Camille, for this EU perspective. Again, some comments on your last slides, introducing the Generation 4 reactors, and also the following slides on the 4 big needs will be, some of those will certainly be subjects of our future webinars. So I have been collecting some of the questions that have come in during your presentation. There seem to be a lot more coming in right now. So let me pick one that came in a little bit earlier, and this one would be for Shannon. What are the US safety requirements for the interface of nuclear system and conventional systems regarding contamination level and regarding feedback on the nuclear system? A very relevant and astute question. Shannon?
Yes, thank you very much for that question. That is absolutely something that requires investigation and analysis. As you likely know, the Nuclear Regulatory Commission is the regulator over our nuclear plants in the US, and any modification of the plant to couple nuclear technology with any user, whether that be for power conversion or for hydrogen production or anything else, must be approved by the regulator. We are working with our industrial partners to perform probabilistic risk assessments to look at any potential new accident scenarios that might be introduced by coupling these technologies to ensure the safety of these systems and to ensure that they will pass regulator approval. Now, you also asked about the potential of contamination. This, in fact, was one of the key questions that stopped an earlier project a number of years ago to utilize steam from a nuclear plant for a food processing facility. There was a very, very small but non-zero chance of contamination if we had a steam generator tube rupture or something like that. And there was a plant in Michigan that caused some concern, not by the regulator, because it was such a minuscule risk, but by the nuclear insurer. So in fact, we do look at these things, and we begin looking at designs, and the designs that we're pursuing currently use an intermediary loop. Heat exchangers, an intermediary loop that separates the nuclear side from the non-nuclear side to bring that risk of potential product contamination to zero. And so this is the approach. We lose some efficiency in the processes there, but it does reduce that risk to zero. And it also brings consumer confidence up with regard to the utilization of nuclear energy to provide what's needed for these processes.
Thank you, Shannon. In fact, there's a very similar question with a more of a European focus. For Camille, maybe, is the licensing of a combined cogeneration plant, for example, nuclear and chemical, an obstacle? And is there a need to account or simulate for the interaction between not the plants, but the safety authorities of both industries?
Well, the nuclear cogeneration is actually the technology which has been demonstrated to work, and there is about 750 of reactor years of operating experience feedback. So of course, for dedicated applications which we are thinking of in the future, like, for example, the cogeneration use of high temperature steam, or in the context of the co-location with hydrogen generating facilities, the dedicated interaction with regulatory bodies would indeed be necessary to clarify the safety-related interfaces, and also to identify the prevention and mitigation measures which will be necessary to implement. Well, in this context, I think it's worthwhile to mention that the recent restart permission has been granted for the Japanese high temperature test reactor, which in fact is a gas-cooled reactor, which objectives also to demonstrate the high temperature hydrogen production via the steam reforming of the natural gas. So indeed, these regulatory topics can be resolved, and this is something which we need to look in the future based on the application.
Okay, thank you. Now I have a question that's relevant to both. It's a technical question about integrating with hydrogen production. How do you deal with the situation you mentioned, load following? I remember hearing it in Shannon's presentation. How do you handle a situation where both the electricity demand and, say, hydrogen demand is at their peak demand level?
That's an excellent question. How do we manage flexibility on both sides of that? We have to set a control hierarchy and understand, is electricity demand and meeting that electricity demand the first priority? If so, then we need to meet that and meet hydrogen demand second. One of the areas of development that we are currently working on is looking at the flexibility of these processes to produce hydrogen. And there's a number. There's electrolysis processes. There are electrolysis processes which are the focus of the laboratory work that we do at Idaho National Lab. There are also thermochemical cycles, which was one of the cycles that Camille referred to with the Japanese experience. They have different operational modes and different minimum operating levels. We are looking at those to understand what is the minimum operating level of high temperature electrolysis, for example. How rapidly can it be cycled? How frequently can it be cycled? How does that impact the lifetime of those electrolysis cells? Now, remember that hydrogen also is an energy carrier and offers us energy storage, such that we can produce more hydrogen when the cost of electricity on the grid is very low due to low demand, or even negative in some regions because of high renewable generation. So when that is the case, we can produce significant amounts of hydrogen and store that hydrogen for later application in electricity production or application by a number of these hydrogen users. That's one thing really very appealing about hydrogen, is it does give us this delayed application potential as a storage medium for this energy. So those are great questions, and we have to work with each of the users of those resources, whether it be electricity or hydrogen, to understand the demands and understand the flexibility of those demands such that we can design them accurately and appropriately.
Thank you, Shannon. I have a challenging European question. There are lots of questions coming in. I'm trying to deal with the influx of questions, so please excuse me if I'm not asking your question right away. There's a lot of competition. This is the question: will nuclear be included in the EU hydrogen strategy that will be released in the next couple of weeks? The draft until now only refers to renewable generation for hydrogen production. Camille, could you try to address that question? It's more of a non-technical one.
Thank you, Matt. This is indeed an excellent question. Well, as you know, in Europe, we have a diversified opinion about the role of the nuclear among the member states, and indeed also about the European institutions. So the fact is that there are member states which are indeed pursuing the nuclear options, and there are even the newcomer countries which are developing very comprehensive plans to start the nuclear programs. But we have also some new member states which are actually phasing out the nuclear. Indeed, from the technical standpoint, nuclear is an excellent energy source to decarbonize the hydrogen production. Just consider that we have currently about 7 kilo of CO2 emissions generated per kilo of the hydrogen. So if we could use the nuclear for the generation of hydrogen, this could indeed make very significant contributions to the reduction of the greenhouse gas emissions.
Thank you, Camille. So we'll go back to a technical question. There's two questions that are very closely related. Perhaps Shannon can answer them, and Camille, if you want to add something, that is of course most welcome. So these two questions are: what major engineering or technological challenges do you expect in such integrations? If you could give a few examples. And another question: is there any specific example of scientific breakthrough required for such integration?
So the question has a lot of depth to it. What are the biggest challenges and what are the innovations? Integrated systems are vast. There are so many different things that we can do with this. As I mentioned in my presentation, in the US, we're investigating many applications of integrated systems, both on the reactor side, and some of those reactors are still in development and have not yet been demonstrated, and many different applications on the end use side. If we want to take small steps for demonstrating these systems to risk and increase confidence, we start slowly. So that's what we're doing with these light water reactor projects, where those will first only include electrical integration. That's something that we understand how to do. It lays a framework and a foundation for the regulatory structure just for co-location, but those don't really have significant challenges on that electrical integration side. When we begin to move toward thermal integration, we need to understand what heat exchangers are most appropriate for connecting both of those processes. What are the intermediary fluids that need to be considered? It's difficult for me to identify a specific technical challenge without characterizing what it is that we're first connecting. Some of these advanced reactors offer great opportunities for high temperature applications, but we have some materials development needs. We have some high temperature heat exchanger design and demonstrations that are required. So I know I sound like I'm skirting the question, but the answer really is it depends. What are the resources that we have up front? What are the end use needs in a particular location? And then we can look at the stepwise approach to achieving the end goal of efficient use of each of our energy resources. Maybe Camille can offer you a more targeted answer to that, but it depends is really a key answer.
Okay, it depends is a very very scientific answer, actually.
Sorry.
So in this case, one of the questions, though, that I might be able to rephrase. Technically, is it possible today?
Yes.
So there are no scientific breakthroughs that stand in the way. Would that be a fair statement?
That is a fair statement. And like I said, that's why we are starting with what we are, with electrical integration of these technologies to demonstrate the flexible operation, to demonstrate how we do this, to give us additional time for the more challenging technical requirements of some of those chemical processes, perhaps, that we're working to reduce the temperature of operation, such that they better match some of the reactor technologies. But we can do this today. And we can develop even further advanced technologies for a few years down the road that will increase efficiencies and even give us a much better, more efficient energy park type of scenario that we can see deployed in the future.
Thank you. So this is a technical webinar, but I must admit that a lot of the questions revolve around the economics. Do we have comparative studies of using renewable versus nuclear for these cogeneration or other applications? I don't want to put you on the spot to make any firm predictions or even more so the public acceptance. There were about half a dozen questions related to public acceptance. So these are other hurdles that potentially are more difficult to overcome than the technological ones. If one of you two want to comment with regard to that area of questions, please go ahead.
I'll let Camille take the first shot if you'd like to, and then I'll add to it.
I'll leave it over to you, and then I may complement that.
Okay, from an economic perspective, that's actually one of the key areas that we focus on in our analyses. So we've worked to develop comprehensive tool sets to allow us to do techno-economic assessments of these different configurations. So we evaluate, will they work technically? If we couple technology A with technology B, will they work under static and dynamic conditions so that they are flexible and can perform in the way that we need them to? And then we wrap that with economic optimization. How will it perform from a net present value perspective? How do we optimize the cost of the products such that we minimize those costs and maximize revenue to these generators, while of course maintaining affordable electricity and affordable energy products to the consumers? The economics of something like hydrogen generation, for example, truly does depend on where it's located. What is the electricity price? What's the scale of production? What's the efficiency based on the type of hydrogen production method that you're using? We've done a lot of comparative studies to look at how nuclear generated hydrogen compares in cost to renewable generated hydrogen versus steam methane reforming. And absolutely, there are scenarios in which it is competitive. If we're looking at low temperature electrolysis, absolutely we can find scenarios in certain energy markets where it's competitive. If we look at high temperature electrolysis, that can't be supported by renewables directly, but can in fact be supported by nuclear technologies, we do see costs for that hydrogen, costs for those products reducing below what it would be for renewable production. If we begin to add in carbon taxes to these different scenarios, then again, we see a significant benefit. But this is one reason why we do a lot of work with our colleagues over at the Renewable Energy Laboratory, so that we come at it at INL from a nuclear perspective and in partnership with some of our nuclear industry collaborators. And we have our partners on the renewable energy side to understand how these technologies can be most beneficial to one another in producing a cost competitive product that helps us to reduce carbon emissions overall.
Okay, Camille, anything you want to add to that?
Well, maybe the second part of the question regarding the public acceptance. Of course, this is a difficult topic. And as we already discussed, this is actually is a diversified opinion among member states. I think that each technology should be actually evaluated on its merits. And when you consider in the context of the affordable, sustainable development, including the United Nations goals for the Sustainable Development Goals, considering that we have actually 1 billion of inhabitants on our planet which do not have access to the electricity, and we have more than 2 billion of the inhabitants which do not have access to the reliable supply of the clean water. I think that the nuclear and renewables, and also the combination of them, can be considered as instruments to support these development goals. And we are looking also at optimizing with increasing share of the renewables, both nuclear capacities and the renewable capacity in such a way that these goals can be achieved. And I think that, as Shannon pointed out, this can be done with further developments and innovations also in a very affordable way. And I think that this should be put among the other arguments also on the table.
Okay, thank you. I have a yes/no question at the end of this. not at the end of the webinar, but this topic. Can we say that integrated energy systems are the only sustainable energy supply option? So is the integration an absolute necessity to make it sustainable? That's the way I understand this question.
I won't say, I don't like absolute questions like that in a lot of cases, because again, I'm going to go back to my trusty answer of it depends. It depends on where it's going. It depends on what the needs are. I don't think there's any single solution that provides us what we like to say a silver bullet, that's just a perfect solution for all. I think there's a lot of solutions. I think each solution comes with a different financial cost and different end results. When we think about energy systems of the future, we can think about coordinated systems that better coordinate with one another via independent system operators. So nuclear talking with those renewable generators and working with the grid operator, or we can have these more tightly coupled systems where those generators are working in a very tightly coupled fashion to produce all of these energy products. Now, if we're looking at a microgrid configuration where we have we aren't connected to a broader grid, we don't have those dependencies and assistance coming from other regions, integrated systems, I think, are key to making those successful. And I think an integrated system with a nuclear technology, such as a microreactor, provides long-term sustainable energy for many years for those remote regions. That may not be the right solution for other applications. We may have regions that have wind every day of the year, and wind can provide a fantastic solution. So I hesitate to answer yes or no to that question without understanding the context. But I do believe in an energy mix. We don't want to rely on just one thing overall. We want to rely on many different technologies to meet our needs in diverse ways.
Thank you, Shannon. We're coming to the end, but I have one more interesting question, also talking about diversity of not just supply, but products. And here's the question. Hydrogen seems to be difficult and cumbersome to produce, store, and move around. Is there any other energy storage media being considered for these IESs? Or is hydrogen, for whatever reason, still a preferred choice?
I've been talking a lot, but I'll take a first cut because I see Camille's still on mute. Absolutely. Hydrogen is something that's at the forefront because it's an energy carrier that can be used in so many different downstream applications. And we see the hydrogen market growing considerably. Many reports are just now coming out. But I don't think it's overstepping to say that our hydrogen demand could grow by as much as 10 times within the next 1 to 2 decades relative to what it is today. So hydrogen's a primary area of interest, but it's certainly not the only area of interest. We're doing a lot of work in thermal energy storage technologies, understanding what technologies are out there, how they can be utilized, whether that be geothermal storage, concrete storage, compressed air storage. There's a number of technologies that we can utilize for energy storage, ranging from thermal to mechanical and chemical storage that we consider, once again, based on where it needs to go and what those energy demands that need to be met look like and how they vary.
Thank you, Shannon. Camille, if you have something to add, go ahead.
Yeah, well, maybe complementary to Shannon's consideration, we can also mention hydrocarbons. So apart from hydrogen, indeed, also hydrocarbons are an excellent energy storage medium. And they are also compatible with the distribution and transport networks which are already existing. So this is indeed an additional option which is attractive and which we are looking at.
Great, thank you. So again, we have a wide variety of potential ways to store the extra energy, either off-peak or thermal energy that is otherwise wasted in the current large nuclear power systems. So with that, we've come to the end of this extremely interesting technical webinar. I tried to push it a bit into the political arena for a while there, and I apologize to my presenters. And I really like to thank them for being such good sports and answering every single question. I must say we had over 40 questions from the participants. And they were very insightful questions. I'd like to tell the participants that those that we were not able to answer here, I will personally endeavor to give you an answer. Somehow I have to ask the technical people how you can be reached. So thanks to the participants, their good engagement through the Q&A panel box. Thank you for the speakers for sharing your expertise and joining us, especially from the US at such an early hour. This has been a great experience for me. It's my first experience to moderate a webinar of this nature. And just to inform everyone, the webinar will be posted online. And we at the NPTDS, IAEA, will hope to connect again at our second webinar, which is in 2 weeks plus 1 day. So it's on 9th of July, Thursday in 2 weeks, and it will be on small modular reactors in integrated energy systems. This is also one of the reasons why I've not asked the SMR specific questions at this webinar. So join us again and save those questions for the next one, where there'll certainly be a hot topic of discussion. So with that, I wish everyone a good morning, good evening, or good night. And again, invite you to our next webinar in 2 weeks.